Welcome to this week's speaker event. Before we begin, if you guys could fill out the attendance form, either using the QR code that's on the screen or the link that Josh just put in the chat, that would be awesome. We have special projects on Thursday, DBF on Monday, and then an internship panel on Tuesday. And we'll have people from Navair, Da Vinci Aerospace, NASA Langley, and Northrop. Actually 2 from Northrop in different locations. So that should be pretty neat. And then the following week after that, we actually have a Northrop Grumman speaker event with the AIAA regional VP, which should be really cool because he's actually an NC State alum as well. So he's super excited about this type of thing. And I guess before I introduce our speaker, we'll probably do questions in the sense that if you can put your questions in the chat during the presentation, we'll go back through the chat afterwards. And then if you guys want to ask any questions with like your face or the microphone, either one, we can do that at the end as well. So with that, I will stop screen sharing. And our speaker for today is Robin Hardy. She is a crash test engineer at the Landing and Impact Research Facility at NASA Langley, which is also called the gantry. So it should be pretty cool.
All right. I will attempt to share my screen. All right, as Carissa mentioned, my name is Robin Hardy, and I work at the Landing and Impact Research Facility. And I guess as I was at NASA Langley, and as I was starting to think about this presentation, I started thinking, how long have I actually been at Langley? And I realized that it's actually been about 33 years, which is actually a really long time. And I guess time flies when you're having fun. But my adventure started back when I was a student at Virginia Tech. Somewhere between the end of my freshman year and beginning of my sophomore year, I decided to apply for an intern or a co-op position at NASA Langley. And my GPA at the time, I want to say, was somewhere between a 3.4 and a 3.6. Wasn't really high enough from what I've heard. I heard NASA was really picky on GPA. But I'll try it anyway, and got my suit on, went to the interview. And at some point during the interview, the fellow said, I see you're active in AIAA. Oh, yeah. And we talked about AIAA for quite a while. And I noticed at the end of the interview, he highlighted my name. He highlighted my name and the fact that I was an AIAA. And needless to say, I then got that co-op position, thanks to AIAA. And while I was there at Langley, I got to have, 5 different rotations there. You can see kind of the 4 listed there. The last 2 were in the mechanical design group, where we used ProEngineer to design lots of things. And what I got to do at the very end was to design a bumper for the crew and equipment translation aid, which is that image that you can see with the astronaut there on the left. It's a way of transporting the astronaut and stuff along the longeron of the space station. It was kind of a concept that we had come up with at Langley. And I actually got to build something that flew into space. And that was, I told you, that was the greatest thing ever. As part of that experience also, while I was an intern, my boss had the idea that when Jerry Ross and Jay Apt, who are the 2 fellows in the front row there of the astronaut picture, as well as Steve Nagel, came to Langley to come see what we were building and how it was coming and kind of get an idea of what we do here at Langley. They went on a set of tours, and my boss thought, let's stick the intern in with them, let her go on the tours too, because she needs to see a tour too. So I got to be wedged between 2, astronauts in the back of a car, chatting and going to scenes, going to see all kinds of things all over Langley. So that was a pretty sweet experience. So at the end of that, when I was given the opportunity to work at Langley, I of course said yes, and I went to work for the mechanical design branch, which was the group that had given me all these opportunities. And I was there for about 10 years, during which I got my master's at Purdue, also in aeronautics and astronautics. And you can see, I guess I should mention that fellow that was my interviewer, I found out later he was a council member for our local Hampton Roads, the AIAA. And if you can see the little chart on it, those are things that I've done at Langley within our Hampton Roads section. And there's kind of a pattern. once you go from treasurer to secretary, vice chair, chair. So the fact that he had been a council member means that he'd been active in AIAA for quite a while. After I worked in the mechanical design branch, I guess I had an opportunity to go and just do a detail in some other places there at Langley to just get cross-trained, get a little bit more experience. And one of those places, the structural dynamics branch, kind of piqued my interest. There was a lady there who worked at this place called the gantry, and every time she talked about what they were working on there, I thought that was just the neatest thing. So in 2001, I moved over to that branch. And but before I get into that, I want to give you a little bit of background on Langley. For those of you who may not know, NASA Langley Research Center started as the first civilian aeronautics laboratory called Langley Memorial Aeronautical Laboratory, founded in 1917. It was part of the original NACA, which was in 1915. And it was actually the first field center when I guess NASA was stood up, if you will, in 1958. So a lot of really cool things have happened at Langley. That movie Hidden Figures, all those human computers, all those ladies that you saw in the movie, those were that story actually took place at Langley. So we had the first African American female engineer. We had Katherine Johnson and Dorothy Vaughan, and we also had the first full-scale wind tunnel. I think it was 30 by 60 feet, built in 1931 on the Air Force side of the base. We have clean rooms to start that we use when we design spaceflight hardware to be able to kind of test it out and look at it and assemble it in a very supremely clean space. We have over 23 wind tunnels. One of the larger ones is that one on the upper right-hand corner, the 14 by 22, and it's kind of on the outside skirts of the base, a big old thing. We also have an 8-foot high temperature tunnel. We have a vertical spin tunnel. We have the National Transonic Facility, the unitary tunnel, the TDT, all kinds of really cool wind tunnels. So if you're into that, we've got it. There's also a lot of other cool things there. There's anechoic chambers. One of our acoustics facility has just a ton of different ways to try to see how the sound can be reduced when it's out there in the air. Like we put all kinds of things in there to try to test them out. We design and build all kinds of things that go into space. One of them was called the LDEF, Long Duration Exposure Facility, which was a way there were all those little boxes or little trays, and the idea was, let's expose all these different things to space and see how they react. We also do a host of earth science experiments, satellites, that we come up with the idea for to measure ozones and aerosols and different things like that. We have machine shops, and we have composite facilities and model shops, and all the NACA airfoils that you guys studied in your early days, and probably even now, all those came out of Langley. So it's a very exciting place. My favorite part is that the Space Task Group, all the original astronauts started at NASA Langley. They were all housed at Langley, or not housed, but they all worked at Langley, including the Mercury 7, the first group of 7 there on the bottom right. In fact, 24 astronauts came and trained at NASA Langley until about 1961-62 when Houston took over it with the Manned Space Flight Center. So if you were to come to Langley, and you were to come in the front gate on Commander Shepard Boulevard, which is that long drive you can see there going from the bottom left up through the center of the page, you would eventually come at the back of the back of Langley. You'd come to this huge red and white structure, and that is our gantry. The gantry was originally conceived in 1962, shortly after, in fact, it was less than 2 years after President Kennedy charged the nation to let's land a man on the moon and return him safely again to Earth before the decade is out. So we were built as a way for the astronauts to practice landing their rocket-powered lunar excursion module. So this big structure is 240 feet tall, 400 feet long, and about 260 feet wide. And since building this thing, we've made a couple changes. You can see kind of in the back left is kind of a U-shaped red structure, and that's a vertical drop tower. And there's also now a hydro impact basin there on the left, kind of on the outside of the gantry. So since 1965, when the facility became operational for the astronauts, we've continued to do landings. As you can see in the center of the page, we've got the Orion space capsule and the sequence of images there. You can see we've done a bunch of tests on them. And we've also tested the Boeing Starliner and the SpaceX Dragon. We did 34 tests actually on the Boeing capsule with its airbags. We've also done a host of general aviation aircraft. You can see in the upper picture there, trying to understand, you have these crashes, they should be survivable, why are they not? So we do landings, which are controlled. You understand this is what we're expecting. Does everything behave the way it's supposed to? Up to things like, this is a little bit more, dangerous condition. What if we landed this way? What would happen? So we do all kinds of different tests. The right-hand side, you can see some of the military aircraft. We've had a long-standing partnership with the Army, done a lot of tests on helicopters for them. So we also, ultimately, we do all these tests to try to understand what the forces of impact are and how those forces translate up through the structure to where the people are. We try to make things safer for the people inside of all these craft, if you will. But we also test ideas of taking away that energy. What can we do? Can we put maybe an energy absorbing floor in the bottom of a helicopter, say in that helicopter section drop test? We had a carbon Kevlar helicopter subfloor there. We put that in there. We did a crash test to see, does that behave the way we think, the way we've modeled it? And does it take any of the energy out so that the energy reaching the passengers is less? So we had a whole bunch of different ideas that we've tested. The bottom left-hand corner, the aluminum honeycomb, that was something that we put in the bottom of the capsule, the Orion capsule. We're going to try to take out some of the energy of impact of that. The right hand, you can see kind of a goldish, that's a Kevlar deployable energy absorber one of our researchers came up with. And it's a pretty neat idea. It's a folded, and the holes there are to kind of let some of the air out. But the idea is that you would fold it, you would put it at the bottom of something that might crash, and when you found that it might crash, you deploy this thing, and then it would then crunch, kind of looking like it does there in the right-hand picture, taking out the energy of impact. So ultimately, all these things are trying to, again, to take out the energy of impact so that less of it reaches the passengers that are inside. So not only do we do, full-scale tests of big, airplanes, helicopters, spacecraft, rocket ships, not rocket ships, airplanes, but we, with our big gantry, but we also have these vertical drop towers. That red U that I showed you before, we've now upgraded so that we have a controlled vertical drop test scenario there. It's kind of in the middle of the screen. And then we also have some indoor drop towers. The one on the far right is the one that's down the street from my building. And we have oftentimes a lot of students. And these drop towers give the students a really good opportunity of something that they can be in complete control of. They can run their tests, and we can just give them guidance a little bit easier than them running a test at the big gantry. So last summer, we had 2 students from Virginia Tech, and their job was to try to do a series of tests on general aviation aircraft seats. We had old seats and new seats, some even newly designed seats. And the idea is that if we get UAVs, if we get little aircraft that individually flown around things, and we want to put seats in them, a lot of these companies coming up with these seats don't have the money to do a big sled test, which is usually what you have to do to qualify a seat. So there must be a way to do a very simple test to be able to qualify these seats. So what we did is we took the bottom half of the dummy and we did a series of tests. The students did a series of tests on these seats. And to give you an idea what that might look like, very simple test. All you need is a drop tower and your seat. And it could be a mass. It doesn't necessarily have to be the bottom of a crash test dummy. But you can kind of see we did a whole bunch of these tests. We had an accelerometer on the bottom of the platform there where the seat was attached, and also on the drop mass to try to gather the energy of the impact and then compare that to what was acceptable for those seats. So to do all these tests, ultimately, as I mentioned, we're doing these tests to try to make things safer for people. So what better way to do that than to have crash test dummies? What you see here is a series of, I think it's 24 crash test dummies that we put inside that big airplane you can see in the background. That was the Fokker 28 test that we did last summer. It was about 27,000 pounds. We lifted her up about 100 feet and slammed her into the dirt at about 52 miles an hour. So we put all these crash test dummies in there. You can see they're different sizes. Some of them have a very stiff necks, some of them have articulated necks, which means that they move a little bit more realistically. We usually put accelerometers in their head and their chest and their pelvis to try to measure the accelerations and then compare that to an industry standard and see how they're behaving and see if what they're experiencing is acceptable, if you will. You can also see a bunch of kids. We partnered with the FAA and also the Army to do the tests on the Fokker. And some of those little people, we have a 6, a 10, and a 12-year-old crash test dummy. And we also got an infant and a toddler from the FAA. And we put those inside the airplane, and we put them, the infant had a car seat and the toddler had a safer strap system. And we wanted to see how those would behave in an actual crash scenario without injuring a child, of course. Also, the green dummies there you see on the far right, those are called Wheelmen, and they are much more intricately instrumented as compared to the rest of the dummies that you see there. And those are Army crash test dummies. They're used for trying to understand what the effects on maybe a landmine might be on Army or personnel as they're, maybe in Afghanistan or something like that. So we put a couple of those guys inside of our airplane. And we also had our obese dummy, who's the fellow sitting here on the pallet. So putting crash test dummies of different shapes and sizes inside of our test article, you can kind of see how somebody of different, how different locations in the airplane they may behave, or how size affects injury. So when we do a crash test, we stay inside our control room. You can kind of see in the upper left-hand corner, that's our control room. The people that run the tests are in there, our instrumentation people, our camera people, our guy who runs the test. And you can also see from the control room a big old white board. And this is called the Lunar Walking Simulator. It also came about back in the 1960s when the facility was built for the astronauts. And the way it came about is kind of funny. Back before we went to the moon, we didn't know if you jumped on the moon, if you would just keep on going, or what would happen exactly. And the story goes that an engineer, and this of course is what engineers do, right? He's laying on his couch, he's watching a college football game, he's pushing his feet up against the footrest of his couch, and he starts to think, now if I was pushing at the right angle, then that might put about 1/6 G into my spine. So the Lunar Walking Simulator, that big white board, was built. And so what we did is we strapped up engineers and technicians and had them walk astronauts on the board and measured the loads in them. We also landed the lunar excursion module on it. Right now, we pretty much just use it as a backdrop for our tests. You can see how this is where the test happened. And just a little side note, all those little smiley faces, upside down smiley faces you see on there, we use those for high-speed photography, photogrammetry. We do a lot of video of the tests that we take, the tests that we do. You saw that big airplane. We only had one big airplane. So we have to capture as much data as we can when we do a test. So one of the biggest things that we do nowadays is capture a lot of video. High-speed video, we put a lot of GoPros around. And with these smiley faces, we kind of track the motion of the airplane or whatever it is that we're crashing with respect to a fixed spot. And you can see that fixed spot is designated as those little smiley faces on the backdrop. So we can kind of track where it's going with respect to those points. So when we do a test, as I said, we stand in the control room, but the way it works is we have a pullback cable, which we attach through the CG of the test article. You can kind of see it. If you look, there's a movable bridge. That pullback cable is attached at that point. And then there's 4 swing cables that come from the upper left of the gantry, the rest vent, we call it. So you pull the test article back with the pullback cable, and then we use explosives to release that cable, this guy right here. And then the test article will swing through the air. Nowadays, it's kind of a parallelogram motion, such that whatever angle you start with is the angle that you should be landing at, unless there's aerodynamic forces at play. And then we swing the test article through the air on those swing cables. We use another explosive to cut those cables and then allow the test article to free fall, hitting either the concrete. We have 12 inches of concrete underneath the gantry, or dirt or sand, or in our hydro impact basin. So here's what it might look like. You just saw the pullback cable release. This is the airplane, the Fokker 28 airplane that I mentioned. So here the swing cable's just releasing, and you can see it didn't go too terribly far. We didn't really know what it was going to do, so we put that big hunk of concrete there in front of the airplane because we weren't sure if it was going to go into our hydro impact basin. So this is kind of what a swing test might look like if you were attached to the test article.
How much did those concrete blocks weigh?
I want to say 300,000 pounds. Yeah, it was a lot. I don't remember exactly though, but yeah, like I said, you can see it didn't go too terribly far, but we didn't know. One of the models said it was going to stop, within a few feet. One of them said, pretty close to those concrete blocks. So here's some more video. As I mentioned, we take a lot of video. So here's what the airplane looked like head on, and from the side, you'll notice that there's a bunch of dots on it, and that again is for our photogrammetric measurements. Actually, in that case, it's a random pattern of dots that we track the motion of. We use our high-speed cameras to track the motion so that we can kind of see where it's going, how fast it's going, things like that. And you can see the passengers there as well. We had a bunch of GoPros inside the test article so that we can track how the people are behaving, how all those crash test dummies are behaving on impact, because we want to take the data from those crash test dummies and compare it with our computer model. And if you can see what they're actually doing, then it makes the data make a little bit more sense. You can see that pretty violent impact for those guys. So on the left, you'll see there, that's the computer model of one of the crash test dummies. You see he's sitting in the seat that's applying gravity to him. But the way that you model the crash test dummy beginning before the test actually happens, of course, affects the way he's going to behave when he impacts. Because where he starts, he's going to move a certain way, depending on if he's leaning a little bit or if he's kind of wedged up against something. So what we're doing now is we've gotten this new Faro 3D scanner, which is kind of like a camcorder on a tripod, and we can put it inside. What we did in this case is you put it inside the airplane. It spins around horizontally, and then there's also a mirror that spins around vertically. And you can capture in great detail. It creates a point cloud of everything that it sees, 360 degrees, and then we can take that data, import it into our computer model, which is, we use LS-DYNA, and if you can see there on the right, that's the two laid on top of each other. So you can kind of see what the changes are. You can adjust the model of your crash test dummies so that they match what's actually there in the test. And then at the end, when you look at your test footage versus the LS-DYNA simulation, you see that they're behaving pretty closely. The seat's a little bit different, and the data not too terribly bad, test versus simulation. All right, now this, as I mentioned, we oftentimes have interns. And one summer, several years ago, oopsie, I did it again. I always do that. One of our interns took a bunch of our footage and made this video. He, by the way, is working at NASA Glenn Research Center. So what you just saw is our space capsule, the Orion capsule, from inside the pool. So as I mentioned, our facility was conceived in 62-63 and was originally made for the Lunar Excursion Module to practice landing on the moon, if you will. So we did a lot of things to try to make this as realistic as possible. In this view, you see a bunch of sandbags, but they also used plaster of Paris dirt to try to create what looked like a lunar surface. They used black spray paint to create shadows, because obviously landing on the moon, there's lots of obstacles you have to avoid. They were concerned that in the dark, the glare of the sun would be odd. We had spotlights. We did a lot of testing in the dark. We put spotlights on the edges of the gantry. We put a big tarp around the outside of the gantry to try to make it realistic as possible. As I mentioned, Neil Armstrong and all those fellows trained at NASA Langley, and somebody asked Neil Armstrong, what did you think about tests? What was it like landing on the moon? And he told somebody it was just like Langley. So we feel we did a pretty good job. Also, he really apparently enjoyed the testing at Langley because he had an almost fatal experience. He had to eject last minute out of one of the simulators simulators, and the airplane exploded. So he kind of barely escaped with his life. So he wasn't really very fond of doing those tests anymore, but he really liked being at Langley because we had big cables supporting the lunar excursion module, and he could do all kinds of crazy maneuvers while still being very safe. So what you're seeing now, in just a moment when I hit glow, that's a fellow running on the ground, and there's another fellow running on the lunar walking simulator. I believe it was 10 kilometers a second or a minute, I don't remember. So you can see that it looks very lunar-like. They supported him with cables. They could do all kinds of maneuvers to see what it would be like walking at 16G. So after 1962, or actually 1972, the facility kind of got a new purpose. We started testing general aviation aircraft. The Learfan that you see there in the picture was actually a pretty cool thing. It was a composite airplane, had a lot of safety things, one of which was an energy-absorbing bar in the middle of the airplane. However, the airplane itself was very stiff, so that energy-absorbing bar didn't get to do its job. So the loads on this thing were actually pretty severe. There were cracks in all the windows, window frames, and we actually decapitated one of those crash test dummies. So sometimes things don't behave exactly the way you expect them to. The airplane that you just saw impact, it was designed to break apart upon impact, taking out the energy of impact. And that thing apparently had a whole bunch of different energy-absorbing things. It had energy-absorbing seats. The engine there that you see flying around was supposedly out of gas, but it obviously wasn't. And again, you learn a lot of things when you do things dynamically. So nowadays, from about 2006, we've been working on space capsules, among other things, and apparently airplanes as well. What you're going to see here is that deployable energy absorber I showed you in an earlier slide. This is at the bottom of a helicopter, a Bell helicopter. We did 2 tests with it, one with the helicopter with the energy absorber, and we also put 4 crash test dummies in there with energy absorbing seatbelts. And we tried to see what kind of accelerations, what kind of forces do these guys see when they land with the deployable energy absorber, and what do they see when we're without the deployable energy absorber. And it actually took about, it was only about 1/3 of the force on the crash test dummies with that deployable energy absorber as compared to without. So it did a pretty good job. Now this was a pretty cool test. We had 15 crash test dummies stuffed in this helicopter, raised at about 10 feet. It wasn't a very exciting test, but it was pretty cool in that we had all these crash test dummies. We had the 2 military guys in the front with the special seat belts. We had them, as you can see, fully instrumented or fully geared up. Again, you see that dot pattern on the outside, and that again is a way to track the motion of the helicopter. We can also use it to find strains in the helicopter. Tracking the motion of that dot, the dots, you can kind of see how they're moving, how they're behaving, and you can see the strains that the structure is seeing during a test. So we did all kinds of really neat things during this. There were, you can see all the crash test dummies in there. The 2 fellows in the front, they were supposed to be like standing guys. If you imagine a military helicopter, you might have some soldiers standing there holding on to the straps at the top. So we wanted to see what kind of flail motion they had. So we actually used GoPros in the front, or not GoPros, Xbox 360 in the front of the helicopter to try to track the flailing motion of those guys. We did learn, though, that when we hit release, they pretty much went airborne, so the flailing probably wasn't as realistic as it would be if you were a real guy, because a real person would probably grab onto things when all of a sudden you were going down. We also did this really neat series of 3 airplane crashes. These were Cessna 172, one of the most popular general aviation airplanes. And these tests were to test on emergency locator transmitters. So we had a bunch of these things put in from different companies, and we wanted to make sure that they sent out the signal during a test, even a very big test, or I guess a disruptive test like this. And if you can hear that little beeping noise, that's those emergency locator transmitters sending off their signal. As I mentioned, we use a lot of GoPros in our tests. We put them on the back of this airplane. You can see it had a pretty bad day, but generally they're not too expensive, so we use them a lot. This is kind of what one of the side slow motion cameras might show you. So you can kind of see what a crash looks like in slow motion. So you can see exactly how it's behaving and compare that with your computer model. Starting in about 2006, we did a bunch of spacecraft tests. We started off with just a basic dish. Sometimes you start very, very simply. Let's make sure we can understand the behavior of the disk. Let's make sure we can understand the behavior of the dirt. Let's try to avoid things like foxes and, in this case, dragonflies, and see how that works. Those little circular dots are, again, for photogrammetry, so we can kind of track the motion of this disk. But one of the things with these Orion set of tests that we were starting here with this disk was, how does the dirt behave? Because what you impact changes the effect on the structure. If you hit something very hard or very soft, obviously the forces that go into the structure are going to be different. So we started off with these very simple tests, making sure we could understand the behavior of the disk, make sure we could understand the behavior of the dirt. And then at some point we were looking at, okay, what if you have this space capsule on top of a rocket and it needs to abort? It's going to abort into the sands of Kennedy Space Flight Center. How does the sand behave? So we did a series of tests with a half-scale space capsule, looking kind of that disk, but stuff built onto it, so it had a more realistic CG. So we did a bunch of tests with that to try to understand the behavior of the sand. Actually very complicated, what we did to the sand, but I can get into that another time. Then we did a series of tests. Now you have the half-scale test article. Now we needed a full-scale test article. It's the same size as a real space capsule, with the right weight. And we did a series of tests with two airbag companies, ILC Dover and Irving Aerospace, to try to see how would these airbags take out the energy of impact and allow us to reuse the space capsule. That particular one, we weren't quite sure whether that capsule was going to flip over. Luckily it didn't. But you can see the airbags are kind of neat. There's an inner airbag and an outer airbag. So the pressure of the outer airbag is set to a certain pressure, and then when it impacts, it's supposed to go up to a higher pressure and then send a signal to the little the explosives that are attached to the ports on each of the airbags, allowing the air to come out. Kind of a little shameless plug for doing testing. When we did those airbag tests, just the vertical tests, the test versus analysis was right on. But when we started doing those airbag tests, where we did the swing tests, where we pull it up and you release it and it has now a forward motion, our tests and analysis weren't matching very well. And they found that, the analysis says that when you hit release on the vent, it's going to release immediately. But in real life, the pressure inside the airbag continued to rise, so that until the vent was completely open. So the pressures inside the airbags were actually a lot higher than the engineers wanted. So we had to kind of take a break and go back and refine this analysis before we could keep going on the tests. So it's really important to do testing so that you can kind of see what really happens, especially as I would say in the dynamic environment. So at one point we, with all these capsules, NASA decided we're going to now land in the water, kind of like Apollo did, but we needed to do tests into the water. So after a while, we decided to build this hydro impact basin. You can see the dimensions there. Oops, oh, I did it again, sorry. Here we go. So we decided to build this hydro impact basin. But before we built it, we had to prove that we knew what we were doing. So what we did, we put a target, we put a pile of dirt where the pool would be, and we put the target, that little baby pool, where we wanted to hit. And we then released the test article using our calculations to show that we could not only release things under the gantry, like all the other tests that you saw, but we could throw something, release it, and it would impact the spot that we wanted beyond the end of the gantry. So as you can see, we have a lot of video. We like to take video. It's data. So you can see what the splatting looks like. But after we did that, we successfully showed that we could hit the target. We were then given the go-ahead to go ahead and build the pool. So the first step was to put those pylons in at the one end of the pool where all the that little square at the end is where our crane goes, where we lift up the test article. So that has to support a lot of weight, and that one end is vertical, so it needs to not collapse. So we pounded those pylons in about 60 feet. And there's about, I think the angle of the pool is about 35 degrees, filled it up with water. It's about 1 million gallons of water inside our hydro impact basin. Took about 6 months to build the pool. So after we built the pool, we had to, of course, test it. So we got a space capsule about the right shape and size, right CG. We filled it with instrumentation, about, I think it was about 250 channels of instrumentation, pressure gauges, string pots, accelerometers, pressure transducers, and we did a series of tests showing that we could release a test article into the pool and that our instrumentation and our data systems would survive, that we would hit the place that we wanted to inside the pool, and that we could actually pick it up. If it flips over upside down, that we could pick it up quickly enough so that we didn't destroy our instrumentation. The video you're seeing now is actually from our technicians are on top of the gantry during a lot of these swim tests. We always have about 4 technicians on top, and one of them chose to have a video camera with them, and he took this footage of what the test looks like from on high. That swinging platform is called the integration platform, and that's what we use to hold the capsule. And this video is actually taken from a GoPro attached to that integration platform. Not a very good scene to see if you've just eaten lunch, but people have actually volunteered, oh, I'd like to swing on that, but no, we're not going to do that. So after we did the boilerplate test article test, we had now a $50 million test article, the ground test article. And what you're seeing here is all of these things happen at the same time. So you can see when it hits the water on the upper right, what it looks like under the water is on the bottom right. And the 2 crash test dummies, that's a 5th percentile and a 95th percentile crash test dummy. That's the range of the astronaut, the sizes that the astronauts could be. And you can see that they're not moving a whole lot during this impact test. It's a pretty benign, gentle test for them to hit the water. So we've also done some other things. This is very unusual for us. All the tests that you've seen have been under the gantry. You pick something up and you swing it, or you pick it up vertically and you drop it. But this test was a little different. We had a NASCAR donated by Petty Enterprises, and what we wanted to do was to try out this soft wall concept, which is kind of that goldish thing you can kind of see in the middle of the concrete block. And this thing was designed with it's a metal plate with foam on the background, and then the whole thing is wrapped in a fiberglass. And the idea is that if a NASCAR would hit the wall, that it would not bounce off of the wall or crunch and get embedded in the wall, but it would kind of gently deflect the wall and then be able to, kind of gently come off of the wall and not be as dangerous as it was before these things were developed. And there actually, of course, there is a NASCAR software now. Now NASCAR does use soft walls. They're not this one, but this was just an idea that one of our guys, actually the same fellow that came up with the deployable energy absorber, came up with this thing, and we wanted to test it out. So what we did is we had a 10,000-pound weight, which we lifted up using the cables of the gantry, and it was attached to the cable, kind of this long cable, which went the length of the gantry attached to the car. We then released the mass, which then accelerated the car into our soft wall at about 65 miles an hour, which is, of course, nothing compared to the 200 miles an hour that a NASCAR might be going. But our wall worked pretty well. We learned some things during this test. When we were practicing, we realized that the car actually doesn't go straight. That NASCARs are designed to kind of go in an oval. So it was aligned to go in an oval. So we had to kind of we have a Langley Speedway outside of the gantry, and we had those fellas come and help us align our car so that it wouldn't go completely off of our soft wall. But it was a pretty exciting test. So if anybody ever wants to be an intern, I thought I'd put this up. The spring applications are going to be due in November 6th. The spring period is from, you can see, January 19th to May 7th. The fellows you see there are the guys that we had work with us last summer. Not only did they help out with the Fokker airplane test, but they also helped us take some soil measurements. They were also helpful in instrumenting our crash test dummies. You can see them there on the bottom. They were instrumenting the pelvis for the seat test that we talked about briefly. The requirements to be an intern at NASA: you have to be a U.S. citizen, you need a 3.0 GPA, but as I kind of alluded in the beginning, the higher the better. Our engineers are very impressed with people who do very well in school, because they figure if you do well in school, you can do well at work. You got to be enrolled full-time in a degree-granting program and an accredited college or university, which of course NC State is. And of course, teachers can also apply. Basically just be 16 or older. For those of you who don't want to skip the spring semester, I put the deadlines there for the other terms, when the deadlines are for the other sessions. As I mentioned earlier, and I know most of you were on when I was talking about this, but we're guessing that the spring will probably be virtual. So most of the engineers at my facility are kind of thinking, well, let's kind of wait and see before we bring on any interns, because a virtual experience when you do a lot of testing like this isn't quite the same. So we're hoping for the summer. And if anybody's interested in that, you can shoot me an email. My email there is at the bottom of the screen. And you can shoot me an email. You can shoot me your resume. I'll keep them on file. And when the time comes that we're looking for interns, I'd be happy to give your resumes to whoever's looking for an intern within my group. So I guess with that, if anybody has any questions, I'd be happy to entertain them.
Well, we did get one question from the chat, and that is, do you know roughly how much a test like this costs?
It's a good question. A test, I want to say like maybe 200,000, but I'm not sure because I honestly haven't been doing that end of it.
How about
I don't know. I'm sorry. The majority of the cost, the gantry itself is basically a big hunk of metal. That's really all it is, with some pulleys attached to it. The majority of the cost is basically paying for all the staff, the people you see there in the picture. That's what it takes to do the test, minus the 3 astronauts. Yeah, I think there's 3 astronauts there. Some of the benefit of doing tests with things that have to do with space, a lot of the astronauts come to watch. But it takes a whole slew of people, and it's really paying for those people that is the majority of the cost. So yeah, doesn't quite answer the question, but I can find out if you guys really want to know.
We actually got another question from Andrew, who says, for people graduating in May, would you recommend looking at the internship or applying for a full-time position?
I mean, I would apply for full-time positions. There's actually quite a few full-time positions that have been advertised during COVID. So we actually have done, I think somebody said it within my directorate alone, and I'm in the research directorate, if you will, which is probably where most of you would work, except for maybe engineering, which is, all that cool stuff I did in the beginning where you use CAD to design things. But within that group alone, we hired 37 people during the COVID period, if you will. So that's pretty good. Actually, would you like me to stop sharing, or would you like me to leave this up?
Whatever you're more comfortable with. It doesn't really matter either way.
Stop sharing.
That works too.
Yeah, that way if anybody has any questions, I can see them if they want to be seen.
I've got a question, Ms. Robin.
Yes, sir.
Is there any security clearance required for your position?
For mine, no. No, actually, I don't have any security clearance. That's a pretty benign job, if you will. Now, a lot of these things, like a lot of times, like when we did those Boeing tests, we couldn't, we had to block the road. We couldn't just let people come down and watch because there was proprietary stuff on them. And the same thing, obviously, with, you would imagine, with the SpaceX tests. We did a series of 10 water impact tests for the SpaceX, and they were very particular on who gets to come down the street. Yeah, we use a lot of math and statics, dynamics, deforms, all those basic things. So if you like those sorts of things and you like wanton destruction, come and work with me.
Thank you.
Sure.
Hi, I have one more question.
Sure.
How much involvement does the FAA have with all these tests going on?
We frequently partner with them quite a bit. In fact, because of the FAA, we were able to do that airplane test. They provided a lot of the funding for that. That plane actually sat outside the gantry from when I began at the gantry in 2001 until last summer. So it was there for 19 years um, before we actually got to test it because somebody decided to take the money away. So partnering with people like the FAA or the Army and different companies like Boeing and all that really is a great thing. So right now we're getting ready to do a bunch of tests with Sikorsky. So they're funding some testing. So yeah, but there's a lot of interaction with the FAA.
Cool. Thank you.
Sure.
What's your favorite test that you've done so far?
I like the water impact tests. I just think the beauty of the water splashing up when those things splash into it is really cool. And then you get about 15,000 gallons of water that go down the length of the gantry during one of those tests. So it's pretty neat, especially when you take one of those tests and put it in slow motion. You don't know the water splash. It's pretty neat. So, and it's just, I have to say though, the airplane was pretty cool because I mean, it was I want to say like a 67 passenger airplane. I could be wrong, but it was up 100 feet. So when you saw that thing, I thought that was pretty neat watching that thing crash because, you know, you look at that thing and it's way up in the air and you think, oh boy, where is that going to go? So there's just such a sense of unknown when you do this stuff that you don't really know. I mean, you think you know what's going to happen, but you don't, you know, sometimes the analysis isn't right. So there's a little bit of excitement to everything. So apparently there was one test where a cable grabbed a telephone pole and ripped the pole out. And so it was a good thing we had the big fence before, you know, between the crash test facility and the building. So, yeah.
With the Cessna 172 test or even the Faulkner test, what kind of G's were these dummies pulling when they hit the ground?
I think they're about 11 from my recollection. Yeah. And I'm actually, yeah, I wasn't involved with either one of those in that respect. So I didn't look at that data, but I think that's what I heard.
Okay.
So, yeah, some of them. I think the pilot did not survive of the Fokker, if you will, but the rest of them did. So not too bad.
His head hit the window, right?
Yeah. Yep. Exactly.
I have a question.
It might have gone under the window even. I'm thinking right.
I had a question about like the space capsule testing. You were saying like you have to get it out of the water quite quickly so that you don't destroy the instrumentation. What type of instruments are on there?
On the bottom of the capsule, we had pressure transducers, and on one of the panels, like you saw kind of where it was coming in at an angle, on this side, we had pressure transducers that you see the pressure of the water impacting. We also had, here's the capsule, we had string pots kind of between like the center of the capsule and the side panels to see how much the panels would deflect during the impact. We had on the GTA test, which was the one where you saw the crash test dummies, I think there was 535 channels of data total, which was a lot, and most of that was accelerometers. We put them everywhere. Some of them don't survive because if you rip the cables, they're not very happy. I think what else? Sometimes we put strain gauges, but generally we're not really fans of strain gauges because in destructive testing, it doesn't take much to rip them off, rip the wires, and then you get nothing. So, but sometimes we do use those. We didn't use them for those tests though.
It's pretty cool. Thank you.
Yeah, it's pretty neat. Thank you.
I had a quick question. How long does it take to like actually plan out for one of these tests before you actually conduct the test?
It kind of changes depending on, I guess, a lot of things. The airplane, I think, we took about a year to get ready for that. That's just because we had the time, and it took a while to get the funding, and so we were kind of planning before we even had the money, if you will. But like the Boeing tests, you know, we maybe have a couple of months before the test article gets there, and then maybe a month to get the test article ready, and then to do it. So we might do, kind of depending on the test too, and just a side comment, like those airbag tests, we might do, if it was a vertical test, maybe 3 of them in a week, whereas a regular airbag, you know, with a swing test, it might be once every 4 days, once a week, once every 2 weeks, something, you know, to do those. So the I guess the amount of testing that we might do in a period changes depending on what the customer wants to. So, and so does the amount of time we have to prepare. Like right now, before the Sikorsky tests, we have quite a bit of time to prepare because we can't do anything. So it's sad.
So that being said, what's changed with COVID? Like, were those Sikorsky and STA tests supposed to be happening in the fall, or how's the timeline changed?
Yeah, the Sikorsky tests were, well, let's say most recently they were supposed to start in July, I think. But now we actually have requested to be on site, to be allowed to go on site to do testing. And it's a whole long 9-step process. Of course, this is the government, right? So it takes a while sometimes. But we are currently at step 3 out of 9, trying to get authorization to go on center. Apparently there's about 900 people out of the 3,500 people that work on center that are actually there doing testing. But we're spending a lot of time, like we're trying to buy the supplies needed. We're trying to design the things that we need to do. We're writing papers. We're doing whatever analysis that we can do before the test. But everything's slipping to the right. So we have two projects currently at my facility that are getting work now. But for example, we're doing more Orion testing. The new test article is called the structural test article on the STA, which is, I guess, more realistic than the original BTA, which was just kind of a hunk of metal that looked like a capsule. And then we had the GTA, the ground test article, which was a little bit more realistic, more expensive. And now we have the STA coming, which is, very, very realistic, very big deal that it's coming to the center. But that testing is going to happen probably starting in January. And the Sikorsky stuff is, it's all going to start going on top of each other. So it's, it's going to keep us really busy come wintertime, which is good. Although it is a little hard to do testing in the winter because of weather, so. But a little bit more answer than you probably asked for.
It's interesting.
Anybody else have any questions? I apologize for talking so fast. Well, if you do, yelping dog. If anybody does come up with any questions, you're welcome to send me an email anytime. I'm happy to answer anything that I can.
All right. Awesome.
Cool.
Well, thank you.
Sure.
Super
Thank you for having me. For your interest. Go AIAA.
Yeah.
And keep active. I tell you, not only can it get you co-op jobs, but it's really nice when you're a full-time, young engineer working in the organization that you guys go to. When I was starting off in AIAA, I was president at one point, and the people that were on the council were like senior leaders of NASA. So you get a lot of exposure to big people, when you're participating in professional societies like AIAA. So keep up the participation, guys.
Awesome.
So thank you for having me.
You got it.